Oops. All right, so let's talk a little bit, again, just to recap. What we've been doing is we've been talking about very simple problem. A function of one variable equal to 0, and the techniques to use to solve them that we may test on are the bisection method. Yeah, you better know that for the test. All right. You better know Newton-Raphson. And you better know secant method for certain on the test. Those, something of that nature is going to be there, almost guaranteed. In fact, probably 2 out of 3. Maybe only 1 out of 3. I don't know. But definitely that's going to be on there. Now, we also learned a couple other methods. One was called fixed point iteration. We learned that one. And we learned anything else? Maybe that was only 4. I thought there was a 5th one. No, maybe that's it. Fixed point iteration. There's other ones. I don't think I covered them, though. I think that was the only other one I didn't cover. Okay, yeah. So that method is kind of clunky, and it diverges badly. So you won't see fixed point iteration on the test. Okay? So you don't have to worry about that. It's not in your homework either. Okay? The ones there in red, bisection, Newton-Raphson, secant, are the most standard ways to solve this problem. Okay? But that's not really, and of course your solver, you know, that's the other way you solve this problem. And you can use your solver on the test. So you might want to know how to use your solver, because if I give you a problem, and you can use your solver to verify your answer. Now, you can't just write the number down without any work and say, well, here it is. You can't do that. You have to show me you know how to implement a numerical method. Okay? All right? But feel free, by all means, to use your solver as a check. To say, oh, I did the numerical method. My answer is 3.8614. And I plugged it in my solver. Boom, 3.8614. I think I'm good. You know what I mean? So feel free to use your solver on your calculator. And by the way, your solver is going to be loosely based on a secant method. Loosely based, meaning that it's a modification of a secant. Okay, that's how your solver works in your calculator. Sometimes the solvers fail, so we have to be careful. Okay? Now, that's a pretty boring problem, though, honestly. What we really want to start talking about is this problem. And that's going to be basically 2 equations, 2 unknown. But basically, any technique that solves that can be generalized to this. You know, basically what we're trying to talk about now is a much harder problem, and it doesn't really have to be to the end. I should really, but I guess we'll say that for now. We'll say that is good for now. I'll talk about we'll keep it to this. We'll just say it's basically, yeah, we'll keep it like this for now. Later on, we'll change it, but for now, we'll say it's n equations, n unknown. Okay? So, n equations, n unknown. How do we solve that one? That one's a lot harder. You got to admit that's a lot harder. I'm thinking that first thing that we spent the last week on, I'm thinking you're kind of like, boring, I can do this, no big deal. I could always graph it, right? That's another thing you could do on the test. You could always graph it. I could graph that. But when you have n equations, n unknown, that's not so easy to graph, is it? In fact, I don't even know if you know how to solve that problem. Okay? Let me give you an example, because we're gonna keep it simple and do a 2 equation 2 unknown, just to keep it simple. But really, the process I'm going to show you applies to more than that. Okay, you can use to more than that. All right, but we're going to keep it simple in the role and scope that we do here. Okay, there are ways to expand this process to multiple, more equations, more unknown. Okay, which we can get into, but I don't know if it's really worth it. Let me give you this set of 2 equations, 2 unknown. Let me give you this set. Equation U, I'm going to make it simpler by saying it's a function of x and y. And it's equal to x squared plus x times y minus 10 equals 0. And I'm going to have equation V, which is, of course, a function of x and y. And it's going to be equal to y plus 3xy squared minus 57 equals 0. Okay? Now, if you got this problem, how would you solve it? Anybody? I wondered, because I was thinking of that myself. Like, if somebody said, solve this for x and y, how would you solve it? Anybody? Anybody know how they might solve it? Substitute? Can you substitute? The problem is both of them have an x times a y. So you can solve either one of them. I guess like you could solve the bottom one for y and try to substitute it, but how do you separate it out such that y is only, you've got that 3xy squared on the bottom, right? So you'd say y, you could solve the bottom one for y. You'd be like, oh yeah, y is equal to what? 57 minus 3x, like that. And then you could try to substitute the other one, but then you still got a y in there. The top one divide by x. Okay, so you take the top one and divide by x, don't you? Then you would get x plus y minus 10 over x equals 0. And that's assuming x is not equal to 0, obviously, but that's fine. We're solve the second one for x. Okay, let's see here. We might be able to do that. Let's see here. 3x y squared, I'm going to do this first, equals 57 minus y. Okay, and then divide by 3. So x is equal to 57 minus y divided by y squared, 3y squared. Okay, and then we could try to plug that into the other one. Yeah, that might work. It gets a little messy, but we may be able to do that one. So we got this is 57 minus y divided by 3y squared x squared plus 57 minus y divided by 3y squared times y minus 10 equals 0. And now you may, do a whole lot of math there. And we may have been able to reduce this down to this. And then how would you solve this? Probably secant method, possibly? Yeah, you possibly could do that. And then once you had the solution for y here, you could then substitute back in. Yeah. In this case, you might be able to do that. You might be able to do that. But I can tell you that there are other cases where that can be pretty tricky. Okay? Because, for instance, if we had another term, see, the bottom equation only has x in one term. But if it had another term of x, y, it could get pretty messy pretty quick. Okay? So, yes, that one looks good. We can do it that way, and that's probably the only way you know how to do it. But I'm going to give you a different method that's going to work in a more general situation, that's going to avoid you having to do more of this. But this is good because, again, you can use secant method on this. If you know how to use secant method on this, you could do it. That's pretty good. So if you're stuck, you don't know what to do, you can do that. But I'm going to give you one that works more generally. And by the way, this is what I figured people would do. Okay, I figured, yeah, that's one way we could do it. But I want to give you one, a more general method. Okay, a more general method. So let's redo this. Let's rethink the same equations. And I think this is in your book, the formulas, because I was thinking about this morning, and I was like, you know, I think this is in your book, the formulas for this. But if it's not, somebody let me know if they can't find these formulas in your textbook, and I will. I mean, I'll send them out anyways, but I can send them out to everybody faster in case they goof this up. Okay, so we're going to consider these two equations. Notice how they're both set equal to 0, okay? So the formula is based on having two equations, u sub xy equals 0 and v sub xy equals 0, which is what we have here, okay? And what we do is we apply a Taylor series expansion to basically to the functions, to u sub xy and v sub xy. And I'm going to spare you all the details because you guys tend not to like all the details. But if you'd like, we could go through the details. But basically what happens, let me just tell you this. I'll give you the background. And if you, I think your book has this. If you have the textbook, I think it has it. But basically what happens is you use a Taylor series expansion. And then you use something called Cramer's rule. Y'all know Cramer's rule? Some of you learned algebra, right? You may have learned Cramer's rule, okay? We're going to talk about Cramer's rule actually a little bit this week, probably, in solving systems of linear equations, okay? But we apply something called Cramer's rule, and you could actually get formulas such that we can iterate and solve for x and y together. Okay, these formulas are somewhat big, okay, somewhat large, somewhat messy, and again, of course, no one's going to memorize any of this. Okay, you'll be given these formulas, okay, but the idea is, can we come up with an iterative way? Now, these formulas, the formulas I'm going to give you are the simplest way of doing it, which is based upon a 2x2, meaning two equations, two unknown, okay? But I want to tell you, these formulas can be generalized to 3x3, 4x4, 5x5 more, okay? In fact, I used to give students the general like 5x5, 6x6 formulas. But then they would get really confused. And so I decided to simplify my teaching of this and say, look, you know, this can be generalized. Okay, you can generalize this to you don't have, this doesn't just apply to 2x2s, okay? This can be generalized to multiple equations, 5x5, 6x6s. I can give you 6 equations, 6 unknown that are like that, and you would never ever want to substitute them. I mean, you'd be lost, okay? You'd never want to do the substitution. In this case, yes, substitution you might be able to get away with, okay? But I could probably tweak that where it'd make it pretty hard. And I didn't tweak it there because I wanted you to see that. Let's say we made it even harder. You don't want to do substitution. There are some ways you can do this. It's basically a Taylor series expansion, and then what we basically do is we're really using the Newton-Raphson technique. Oops. We're really using the Newton-Raphson technique. Okay? This is basically an application of that Newton-Raphson technique that I told you before to multiple equations, multiple unknown. Now, I'm going to give you a power to do something that your calculator can't do, I don't think. Maybe it can, but it may not be able to do it. Okay? And this is much more of an advanced solving tool. Okay, now again, these formulas are only for a 2x2. And on a test and on the homework, you have a homework problem that uses this. They're only 2x2s, but you can generalize this to more. Okay, this can be generalized to more. Okay, so but the formulas I'm about to give you are only for 2x2. I would encourage you, yes, write these down, but it's a little messy. Write these down, but verify this with your textbook. Okay, that you wrote it down correctly, because one little goof could get it all messed up. Okay, and that's what's frustrating about this. All right, here's what we have. We have, this is the first formula. Xi plus 1 is equal to x of I minus u partial v with respect to y minus v partial u with respect to y, all divided by partial u with respect to x. Oops. Partial u with respect to x times partial v with respect to y minus partial u with respect to y times partial v with respect to x. Whew. That's the formula. That's the formula. And in the same way, you can do it for y. Partial u with respect. I'm sorry, that's a v. I'm sorry, that first is a v, not a u. I knew that was wrong, because it's pretty much backwards. Partial u with respect to x minus u, whoops, that's a u. U partial v with respect to x. But the bottom is the same on both of them. The bottom is the same. So it's partial u with respect to x, partial v with respect to y, minus partial u with respect to y, partial v with respect to x. Whew. These are not fun, right? Some of you might think it's fun. But those, that's the formula. That's the simplest way I can do it, honestly, is to do it like that. Write these down, but verify this in your text. And I'll send you an equation sheet here shortly, within the next few days, that'll have all that. Okay? By the way, just a little general note. I give you one of these problems in your homework. Okay? I believe it's problem number 7 in your homework. Uses this. Okay? I actually designed that problem thinking that you were going to write a computer program to do this. Some of you will say, I never want to write a computer program ever unless I'm absolutely have to. I want to do this by hand. That's okay. I'm just warning you now, it takes a little while to do by hand. Just warning you, it takes like an hour, okay, probably to do by hand. If you could do it on a computer program, it can be done much quicker, okay? Now you might be like, oh, that's, no, not for me, it will be not quicker. But I'm just saying, you know, you might want to strongly consider doing that. But no one has to. You're not required to at all. Just telling you it's going to go faster as long as you're at least a little bit comfortable writing the code. Okay? And let's go over this example. Let's go over this example now. Okay? Let's do this example right here. Okay? Let's do this example and implement this. And you'll see it's really not that hard. It's just messy. Okay? All right. So what I'm going to do, let me do this. We got the formulas there. I'm going to have to let's rewrite the equations here again. We got u is equal to x squared plus xy minus 10. V is equal to y plus 3xy squared minus 57. And they're both equal to 0. You have to set them equal to 0. Okay? And what we're going to do is we're going to guess. We're going to start with a guess of what is the x and the y that's going to make this work. We don't know. We're just going to guess an initial x of 1 and an initial y of 2. You have to guess. You don't know. You don't know what x and y, okay? The good news is, in general, with these Newton-Raphson type techniques, as long as your guess is somewhere in the ballpark, usually they're fairly convergent, okay? Your odds of convergence is not too bad, okay? If your guess is way off of the solution, you may diverge or you may converge to some other solution, okay? That's the thing, too, is that this can be applied whether it's linear or nonlinear. These are nonlinear equations here. Okay, you see those two equations? Those are nonlinear. Why are they nonlinear? Does anybody know why they're nonlinear equations? There's several reasons why. Why are they nonlinear? What's that? The squared. That's one of them, yeah. If they're linear equations, you can't have x squared. You just got to have like 3x and 4y and stuff like that. And then you also can't have x times y. Okay, you can't have x times y. That would make it non-linear as well. Okay, these are nonlinear equations. These are like the nastiest stuff that we're going to deal with in terms of solving equations. Okay, I'm actually starting with the harder problem, not the easier problem, which is a little weird. You would think I would end with this problem. But the reason I'm doing this problem now is because it actually, if you look at it, it is applying the tools of Newton-Raphson that I've already taught you and just doing it, extending it to this two equations, two unknown. So you might look, wow, that's a lot harder of a problem. You don't look at that and go, well, the answer is not obvious, right? I mean, you can look at it and go, well, hold on a second. I don't think x squared plus 10xy minus 10, right? If you look at that, x can't be a really big number. And it also can't be a really large negative number, because if you square it, no, it's going to have to be like somewhere between, minus 5 and 5 or something like that, probably. Unless y is way off. Y could be like, I don't know, but it looks at it like, it's probably not too big. Okay? So, how do we do this? Okay, first step is to do all your partial derivatives. Okay? Now, most students I know in the past are fairly comfortable with partial derivatives. It's like when you take Cal 3, Cal 3 has all these like parts that feel really uncomfortable and nasty, like curls and things like that, and divergent. And you do all these things with vectors in Cal 3, and you're like, what the heck am I doing? And then all of a sudden they start pulling out partial derivatives, and you're like, oh, I can do this. A partial derivative. Oh, yeah, that's easy, right? That's what I thought when I took Cal 3. Maybe it's different for you, but I remember when I took it, I was like, oh, partial derivatives. Oh, that's not actually that hard. So help me here. We got to get 4 different partial derivatives. Partial u with respect to x. We got to do partial u with respect to y. We got to go partial v with respect to x. And we got to go partial v with respect to y. And I don't think any of them are that hard. What's partial u with respect to x? 2x plus y. Bingo. What's partial u with respect to y? Somebody else. You can do this. Partial u with respect to y. X. You guys are good. See, you love these partials. Partial v with respect to x. Somebody else do it. Three y squared. Partial v with respect to y. Somebody in Fort Walton, tell me that answer. Partial v with respect to y. That's a little harder, but not too bad. Somebody in Fort Walton, what's partial v with respect to y? Somebody. Unless you're saying it and I can't hear you. Which is entirely possible. Yes! 1 plus 6x. No, not exactly. You're close. You're very close. 1 plus 6x y. Yes. Y'all see where I got those? I think partial derivatives are generally pretty easy to students. You like those. Like I said, like one thing in Cal 3 that they started pulling out, I'm like, oh, these are pretty easy. Yeah, I can do these. Okay. So we did all the partial derivatives. Now the fun begins. Let's evaluate each one of those partial derivatives at our current initial guess. Okay? Let's do this. Let's evaluate now. I'm going to just go through these pretty quickly. I think you can do these. We can probably do them all in our head. Partial u with respect to x is 2x plus y. If x is 1 and y is 2, then that sure looks like 4 to me. Partial u with respect to y is x. Well, that's just 1. Partial v with respect to x is 3y squared. Y is 2. 2 squared is 4. 4 times 3 is 12. Partial v with respect to y. 6 times x times y. X times y is 1 times 2. 1 times 2 times 6 is 12. 12 plus 1 is 13. Right? We can do those. So now I did all that. The only thing left I have to do is substitute in, except one more little thing. These formulas also require me to substitute the values for u and v. What are u and v at my guesses? That's the last thing I have to do. If I have u and I plug in the guesses, look at my equation there in green. If I plug in x equals 1 and y equals 2 for u. Okay, let's do that in my head. 1 squared plus 1 times 2, so that's 1 plus 2 minus 10. 1 plus 2 is 3. 3 minus 10 is minus 7, right? So this is negative 7. And v, last one, plug in 1 and 2 there for the v equation. Okay, so this is a little trickier. We got 2 plus 3xy squared. 3 times 1 times 2 squared, because y squared is 2 squared, so that's 4. 4 times 1 times 3 is 12. 12 plus 2 is 14. 14 minus 57. What's 14 minus 57? Negative 43. Okay, good. So now the rest of this is what we call plug and chug. Okay, right? And what we do is we plug and we chug because we just got to put these all in. So let me write it out. X to the I plus 1. I guess you could call this really, if you really want to be honest, this is really x1. x1 is equal to x naught. X naught is 1, right? 1 minus u times partial v with respect to y. So this is minus 7 is u times partial v with respect to y 13 minus v, which is negative 43, times partial u with respect to y. Partial u with respect to y is just 1. Okay? And then you're going to divide by each one of these. Partial u with respect to x is 4. Partial v with respect to y is 13. Minus partial u with respect to y is 1. And then partial v with respect to x is 12. Okay. So now we do some cleanup here. Let's see here. The top is 13 times 7. What's that? 70 plus 21. So that's minus 91. Minus 91, basically plus 43. And I think we can do the bottom here. 4 times 13 What's that? That's 26 times 2. What's that? 52. 52 minus 12 is 40. So I think the bottom's 40. So what's minus 91 plus 43? What's that? 47. Negative 47. 48? Yeah, minus 48. Okay. So this is really equal to, one is minus 48 divided by 40. That's not too bad. Okay. So that's basically equal to 1 plus 48 40ths, which let's go to Matlab now because it's getting messier to me. Maybe we probably could do that in our head actually, because 8 40ths is what's that, like 1/5? 2.2. Yeah, the whole thing, if you just do it, is 2.2. Okay. Everybody see how I got that? Albeit a little bit nasty, but not that bad. Like, I think you could probably do this. Now, if on a test, I can't have you do any more than 2 iterations. I mean, it just take too long, okay, on a test. You know, I'd like you to do 2 iterations just to make sure you know what to do. Now, I haven't done the y, so let's do the y. Let's do the y. In fact, when I first did this, I would only do the x, because the y to me seemed kind of redundant. It's almost the same thing, you know, just a little different. And the students would get really mad at me. They're like, "You've got to show me the y." So okay, I'll show you the y. All right. So okay, so we got the y. y1 is equal to, in this case, let me draw a little line here to make sure we're separating this out. Here's our answer. Okay, y1 is equal to our initial y. We're going to guess 2 minus, and by the way, the bottom is the same. The bottom is the same. I'm going to write it out. The bottom is the same on both. The denominator is the same on both of them. So I can just write it the same as the one I did for x up there. It's exactly the same. The top x, the bottom y, see, they're the same denominator. It's the same thing. The top is different. It's going to be v sub I, so that's going to be the minus 43 times partial u with respect to x, 4, minus u sub I, which is minus 7, times partial v with respect to x, which is 12. Okay? So if we do this math, we get 2 minus, okay, 43 times 4. We can do that in our heads, right? 40 times 4 is 160. 3 times 4 is 12. So isn't that going to be minus 172? And then you're going to add 7 times 12, which is 84, minus 172 plus 84. Ooh, what is that, like 88? And minus 88? No? What's minus 172 plus 84? Is that minus 88? Okay, I was right? Okay. Minus 88. And the bottom is still the same. It's still 40. So if you do this, what is that? 88 40ths. That's 2 with another 8 40ths. That's another 0.2, right? So isn't this 4.2? I think if you work it out. I may have goofed. I'm doing it all in my head really quick. I think you could do this on a calculator pretty quick too. Okay? So what I'm saying is that I think there's 2 things. One, this is a nice and quick way to solve 2 equations, 2 unknown. Even how nasty they get, you should be able to do this. The other thing that's good about this is it can be put in a computer program. Okay? And by the way, Matlab does have tools to solve this kind of stuff. And how does Matlab solve? If you have a solver in Matlab or any of these advanced solvers, Wolfram Alpha probably has one too. these advanced solvers basically use this type of technique. Okay, advanced solvers basically use this type of technique. Okay, so now we're going into the realm. I mean, if you could go way into this and get into grad school and spend years working with advanced equation solvers. Okay, but we're not going to do that. We're just going to say, okay, yeah, we know how to do this. Okay, we know how to use a solver more than just the one equation, one unknown. We have the tools to do this. By the way, if you want to do this again, okay, let me just be clear. If you want to do this, the next iteration here, okay, because we're not done, right? The answer is not x equals 2.2, y equals 4.2. Let me be clear. That's not the answer. You have to iterate, okay? You have to keep going. Make sure that's clear. Keep going. Right now, use x1 equals 2.2 and y1 equals 4.2. Okay? And be careful here. You do have to recalculate all of the partial derivatives. See how I calculated all the partial derivatives over here on the left-hand side of the page? Those would have to be redone, right? You would have to redo those. You all see that? It's not, on the next iteration, partial u with respect to x is not 4 anymore. Partial u with respect to y is not 1 anymore. Okay? In fact, partial u with respect to y is x, right? You see it over there on the right? Partial u with respect to y is x. So partial u with respect to y is now going to be equal to 2.2, right? If you do it again, just trying to make sure we're clear here, that's now going to be 2.2. You see, this formula is still the same. That's still the same, but you have new numbers you have to substitute, right? All of these have to be redone. But if you had a computer program, you could do this pretty quickly. If you could do this in Excel, a spreadsheet could do this really quick. You all have a spreadsheet. It can be done in a spreadsheet. Yeah.
Keep going until the numbers equal each other.
What will happen is they'll keep going. It'll converge to the answer. Okay? It'll converge to the answer. I believe the answer is 2 and 3. I believe if you keep going, you'll get x is equal to 2, y is equal to 3. I think that's the answer. I think so. If you keep going, the next x will get a little closer to 2, the next y will get a little closer to 3, and you probably have to do it like 3 or 4 times. Okay, you probably have to do it 3 or 4 times. Once you get it about 3 or 4 times, then all of a sudden you'll see that the numbers are getting really close together. Like, how do you know when you're good? Look at approximate error, right? If you do it and you run it and you get x is equal to 2.001 and y is equal to 3.004, and you run it again and x is equal to 2.00001 and y is equal to 3.00042, you kind of go, oh, I get it. They're converging, right? You can see the convergence, okay? And in this case, I believe it converges to that, okay? If you keep going, okay? If you keep going. Normally, the good news with this technique, by the way, is that it doesn't take that many iterations. On your homework, I asked you to do 4 iterations. Okay? I asked you to do 4 iterations. So, yeah, if you want to do that by hand, you can do that, but you might want to use a computer program. Okay? Because this could all be thrown into a computer program fairly easily. Or do it in Excel. If you guys want to do it in an Excel spreadsheet, gosh, this could be done in Excel so easily. Because all you'd have to do is put in the formulas, and then all you have to do is copy and paste the formula down on columns, and then have your new x's and new y's in different columns, and just set it up as an Excel spreadsheet. It could be done really easily.
This will be on a test, right?
Yeah, this will be on a test. But again, if I do it on a test, I'm only going to ask for 2 iterations, and it probably won't be this. The equations will probably be a little simpler. They will be. Okay, I'll just tell you. They're going to be a little simpler so that it goes faster. Okay, it'll be a little simpler equations. So a little simpler equations, a little simpler to run through. But same process. And again, you don't have to memorize these 2 equations I boxed in red. You're not memorizing. You're not memorizing, okay? Not memorizing, right? But this is a method we can do to solve a fairly nasty problem, okay? Which is function of 2 variables that are totally nonlinear like this. And yes, I haven't shown you this, but this method can be generalized to solve multiple equations, multiple unknown. This can be generalized to 5 equations, 5 unknown, 6 equations, 6 unknown. Okay? One of the reasons I haven't shown you that is because we haven't gotten into all of that in linear algebra yet. Okay? And that's what we need to spend some time with over the next few weeks. Some of the linear algebra we're going to cover before the test, and some of the linear algebra will be on the next block 3 homework. Okay? But what I want to do now, and for the next few weeks, is give you a primer on linear algebra. I will tell you that this will be very helpful for you in your classes. It will also be very helpful for you to understand things in the future. Most programs don't have enough room to offer their own linear algebra course. You may have done some linear algebra in DiffEq, I don't know. DiffEq does usually have some linear algebra in it just because it's so important to solving differential equations. But your linear algebra that I found, I don't know what your backgrounds are, but most people don't have a very strong background in linear algebra. And so it's important that we work with that, okay? And so let me get talking a little bit about that, okay? You know how to use this technique. By the way, the formulas should be in your book. If you can't find them in your book, let me know. But I think they're in there, those formulas I introduced. I think they're in there. Okay, so now I'm going to go from a hard problem, and now we're going to talk about an easy problem. And I'm going to go from something that looks pretty hard. I bet maybe you thought that was kind of hard. And now I'm going to talk about something that actually I think is pretty easy. And I think you're going to think it's pretty easy. Maybe. I don't know. Okay? How would you solve this? This could happen I know this could happen on a circuits test. You could also get this on a statics test. It may not look just like this, but you get this kind of problem either on a circuits test or a statics test or in other tests. Definitely could come up in several courses besides that, but I've seen these types of problems on either one. There it is. Let's say I asked you to solve this. Besides substitution, which I know some people would do, and by the way, you could certainly do substitution here. But substitution is going to take some time. And this is one of the things I've seen when I've taught students statics before, is in statics, we often get this type of problem. 3 equations, 3 unknown. Linear, just like this. This is 3 linear equations, 3 unknowns. These are supposed to be pretty easy to do. And if I gave this to you on a statics test, or you got this on a circuits test, we're not actually expecting that you do this in substitution. Because honestly, in substitution, this is going to take you 10 minutes you're going to blow on solving this where you don't have the time. Okay? You probably don't have the time. Okay? You don't have the time to waste 10 minutes solving that on a circuits test or a statics test. Some of you may take 15 minutes doing substitution to solve this. Without substitution, what's another method to solve this that somebody's actually used before? James?
I'm pretty sure there's a program calculator. You treat that as a matrix and use CLR, I believe.
CLR?
It takes, you just said,
What are you talking about, Matthew? Multiply through by a number? What is it? Elimination, but that's substitution. I'm doing it again. I never know how to turn you guys without doing that. Okay, I'm hearing some good words, matrix, and I think that's kind of where you were going. Are you sure it's not REF?
Yeah.
I think you're talking about REF. Anybody use REF before on their calculator? Oh, just one time? Okay. Was it on a test or just a homework? Or just for fun?
I think that's my point.
Oh, okay. But you're not totally sure because have you ever used it before?
Yeah, I used it back in, I think it was Calc 2.
Calc 2, okay. Yeah, maybe so. Okay, Matthew, you said matrix algebra. Like specifically, what are you using? Cross product? Are you talking about, it sounds like you're talking about determinants or something. Are you talking about that thing where you go like this? Remember the math teachers do that? Isn't that determinants? Of course, determinants could be you could be using Cramer's rule. Anybody remember Cramer's rule? Like, if I say the word Cramer's rule, does that ring any bells in here? Bells are rung. Like I sort of, kind of, maybe remember my math teacher talking about that in high school. Kramer's rule. Okay, that one did involve determinants. Okay, that did. Okay, but honestly, this is a problem. Not exactly these numbers, but this is the kind of problem you're going to see in statics, or in circuits, or in dynamic systems, possibly. Actually, I could come up with fluids problems that could use this. Yes. Heat transfer problems could use this as well, perhaps. I could come up with heat transfer problems. There's definitely times where this is a very fundamental thing to solve. I'm hearing the right things. RREF is right. Okay, you can use RREF. In fact, I'm going to show you how to use RREF in a moment. Okay, but you want to know the fastest, quickest, easiest way to do this, probably for most of you, is use it, put it in the calculator. But what are you doing in the calculator, Matthew? What are you doing? You said put it in the calculator, but what are you doing? Do you have a matrix solver in your calculator? Okay, so you have that, and you know how to use it? Good. Okay. Sorry, I honestly don't know how to use it. Okay. Honestly, I think, I'm not going to show you this right away because I have a reason and a purpose not to, but I'm going to say the fastest way to solve this is something called a matrix inverse. Ah, yes, there you go. That's the fastest, I think, okay? And that's the fastest for you is a matrix inverse, which I will show you, of course. If I don't get to it today, certainly on Wednesday, you will see this, okay? The matrix inverse, okay? That's probably going to be the fastest way to solve this problem, okay? What I'm going to show you today is another method you could do. Because what if you didn't have a fancy calculator that could do this matrix inverse? And what if you just had a very simple calculator? Or what if you didn't know how to use the matrix inverse? Or what if this isn't even solvable? Okay? What if when you try to put this in your matrix inverse, you get an error? What happens then? I'm going to show you a way to handle it that's going to be more informative. Okay? So what I'm going to do here is we're going to do a process called Gauss Elimination. And the good news about Gauss elimination, even though it is a little bit harder to do, I mean, it's not hard. Gauss elimination actually is really easy. Once you get the hang of it, this is very easy. The thing about it is that it actually is more powerful than a matrix inverse. It actually can give you more information from doing Gauss elimination than it can be by just directly plugging this into your calculator. I can tell you more than just calculator can. Say, really? Yeah, I can. I can tell you more than what the calculator does. Okay, so how do we do Gauss elimination? It's really easy. First thing you do is, let's say you've got this 3 equations, 3 unknown like this. We're going to put it into a matrix form, okay? So all we have to do is do this. Okay? I'm going to write these as a matrix. All I'm going to do is write the coefficients. Okay. Do you see how I got from those equations to the matrix down below? It's pretty easy, right? All I literally did is I'm just dropping the x, y, and z, but I'm just writing them all as numbers, the coefficients, like that. You see that? Very simple, right? You can do that. Now, by the way, if you want to, you can use your calculators on this matrix and do RREF, or maybe it's REF. I'm going to show you this in Matlab in a moment, okay? But I'm going to show you Gauss elimination, okay? And this is something that you have in your homework, and this is something that you should be able to do on a test. Okay, here's the key to Gauss elimination, okay? Here's the key to Gauss elimination. The key is to identify the lower triangular part of the matrix. It's right here, okay? How do I know it's there? Because the first thing I want you to identify is the main diagonal, which is right here, That's what we call the main diagonal. That's the main diagonal, which is always, it starts from the upper left-hand corner and just works down, just as shown. Anything below the main diagonal is called the lower triangular matrix. Lower triangular. Anybody in here colorblind? We're all good? Okay, I always wondered that because I used different colors. I had a student, a female student, and it's very rare for women to be colorblind. But she was colorblind, and she never appreciated my different colors because she's like, those two colors look exactly the same to me. This red and that green, they looked exactly the same to her. I thought that was interesting. You know, I didn't even think about that. You know. Okay. Anyways. Okay. So the lower triangular and the main diagonal. And here's what we want to do. The goal of Gauss elimination is to turn those three terms that I have in green there to 0. I want to make those all zeros. So, well, I could just turn them into zeros real easily. I'll just erase them and make them zeros. No, you can't just do that. Turn to 0. How do you turn them to 0? You turn them to 0 by using add row 1, which I'm going to call R1 plus R2 to get a new row 2. I should be careful. It's not like you, let me back up. It's not just any row 1 or 2. It's really A times row 1, B times row, any kind of combination of row 1 and row 2 together, and I'll show you, to make a new row 2, and then a combination of row 1 and row 3 to make a new row 3, and then finally we're going to add a combination of the new row 2, which we'll call R2 star, and row 3. This is the new R3 to make an even more new R3. Okay, now that looks messy, but in reality it's very simple. Okay, it's basically just a linear combination of each one of those. Okay, it's actually really simple. The way I do it there makes it sound more complicated than it truly is. Let me show you. Okay. So first thing I want to do is I rewrite my top row because I don't change my top row. I don't need to mess with the top row. So I just rewrite the top row. I don't need to mess with it because you never need to turn anything into zeros on the top row to do Gauss elimination. Just write it down. You're good. Now let's take a look at that second row. Take a look at the second row up there at the top. 4, 1, minus 1, minus 3. The goal here is I want to turn this term right here, see that 4 there? I want to turn it into a 0. So how can I add a combination of row 1 and row 2 to turn it into a 0? Okay, if I multiply the bottom row by 2, I get 8. How could I add that to the top row? Yeah, you have to use a combination of row 1 and row 2. If you use row 2, you can do row 2 and row 3. The problem with that is you can get yourself messed up really quickly. So it's better to use the technique I have there on the side. Use row 1 and row 2. Then, if you could do row 2 and row 3 really quick together, the problem with that is that you have to then be careful to write those down on the next step, because and just be very careful. If you do it the way I do it, you tend to make less mistakes. When students do it like jumping around in different rows, they tend to goof up and not rewrite everything.
How about -4R1 plus 5R2?
Beautiful. That's awesome. That's exactly what I wanted to do. So, what if I did this? I said minus 4 times row 1 plus 5 times row 2 gives me a new row 2. There it is. Now, watch with me when I do the math. What's minus 4 times 5? Minus 20, right? Plus 5 times 4, 20. So now, as I hope, I've made this a 0. Now you have to do that same combination on all the other terms of the row. So let's do them. They won't be 0 probably. So it's, take a look at the next column there. 2 and 1. You see the 2 and the 1 there in the next column over from the first column, right? The second column, 2, 1. So it's going to be minus 4 times 2, which is minus 8, plus 5 times 1. So minus 8 plus 5 is minus 3. Okay? Then we got here minus 4 times 1, this is minus 4, plus a minus 5 times, this is minus 1 times 5. So it looks like it's minus 4 minus 5. I think this is minus 9. And then finally you got 3 times minus 4 is minus 12, plus 5 times minus 3 is minus 15. So it's minus 12 minus 15. I think that's minus 27. You see that? Yeah.
Does it matter which one you make negative? The negative 4 or the negative?
No, yeah, because somebody might say, what if I did it 4 times row 1 minus 5 times row 2? Perfectly acceptable. Yep. The only difference is actually all those terms would be positive. Notice I have 0, minus 3, minus 9, minus 27. If you did it the other way, it'd be 0, 3, 9, 27. Perfectly fine. Okay. So, and by the way, if you ever don't like all these negatives, you could always multiply any row by minus 1. That's always acceptable. You can take any row in here and multiply it by minus 1 at any time. Doesn't matter. Doesn't change anything. Okay, so let's do the last one. How would I do a combination of row 1 and row 3 to get rid of that 0 there at the bottom of row 3? First column. I think you guys can get the idea, right? How about this? 2R1 plus 5R3, replace R3. That seem reasonable, right? So let's do it. 2 times 5 is 10, plus 5 times minus 2 is minus 10, so 10 minus 10, 0. Good. Now do the rest of them. 2 times 2 is 4, plus 5 times 3 is 15. 4 plus 15 is 19, I believe. Right? That looks right. Okay. Next one is 2 times 1 is 2. 5 times plus 5 times minus 3 is minus 15. So 2 minus 15 is minus 13. And finally, 2 times 3 is 6, plus 5 times 5 is 25. 6 plus 25 is 31. Okay. I think we got it, right? Okay. So now, one more thing we got to do. One more thing we got to do. Notice I have zeros in 2 out of the 3 lower triangulars, right? 2 out of the 3. The only one left is that one, right? And notice what I suggest you do. Use row 2 now. Why would I use row 2 and not row 3? Sorry, row 1. Why would I use row 2 to change row 3 and not go back to use row 1 here? Why wouldn't I want to use row 1 to try to change row 3? Anybody? Or are you just trying to get through the last few minutes of class going, man, Gauss Elimination. Whew, we're really doing this? Yeah, why not use R1? Yeah, I think you guys got it. Yeah. Basically, if you use row 1, you're going to screw up the 0 at the beginning of row 3. Y'all see that? If you use row 1, you're going to screw up that 0 at the beginning of row 3. That's why we use row 2, because row 2 has a 0 at its beginning, and row 3 has a 0 at the beginning, right? So any combination of 0 plus 0 is always going to be 0, right? I don't care what combination of 0 plus 0 you give me. 8 times 0 plus minus 3 times 0, 11 times 0 minus 8 times 0. No matter what you do, it's 0, right? So that's nice. That means that you can focus on just the last term. Okay, so let's go through this. It's easy. First, we're going to write down the top 2 rows again. 5, 2, 1, 3, 0, minus 3, minus 9, minus 27. And now, I'm going to write this 0 down because I'm not going to change it. What combination of row 2 and 3 is going to make that next term a 0? The next term I'm just about to write, it better be a 0. So what combination of row 2 and row 3 is going to make that 0? What do you think? I got to turn that 19 into a 0. How about 19 row 2 minus, or is it plus 3 row 3? That'll work, right? Replace row 3. Right? Hang with me, we're almost done. This is not hard stuff. Hang with me. We got 5 minutes left. We can do this. We can do this, right? Okay, so now let's do this. 19 times minus 3 is whatever it is, plus 3 times 19, right? That's going to make that a 0. We know that's a 0. Now let's do the other ones. The other ones get a little messy. May have to use, you know what? I'm going to fire up Matlab anyways. Because, where's that? Why can't you just search me? Whatever. Let's do this. I'm going to fire up Matlab just to help me do a couple of these last ones here. Because the next one I have to do is 19 times row 2. 19 times row 2, which is minus 9. So that's going to be 19 times negative 9. That's minus 171. And then it's going to be plus 3 times minus 13. That's minus, so it's, yeah, 19 times negative 9, and then 3 times 13, negative 13. 3 times negative 13. Okay, so it's minus 171, minus 39, I think. I think you get minus 210 if you do the math. And the last one, also kind of messy. 19 times minus 27. Oops. You'll see it gets easier. Minus 513 plus 3 times 31. So you got minus 513 plus 93, minus 420. Okay, that looks messy, but it's really not. What are we saying here? This is, now we're done. I present to you actually a very, very easy way now to solve for x, y, and z. These equations here are very easy now to solve. You might say, really? Yes. Because here's what it's saying. This first row really represents x. The second column represents y. And the third column represents z. Okay? So what this is really saying here is this. This bottom equation is really saying minus 210z equals minus 420. What's z? It's 2, right? Very easy. Everybody can see. Z is equal to 2. Okay? Now, take a look at the second equation there, which I'm going to put a green arrow on. Right there. That equation is saying minus 3x minus 9z is equal to minus 27. That is also easy to solve. Why? Because look, I already know what z is. Oh, sorry, y. Thank you. Y. Minus 3y. Thank you. Minus 3y. Not g. Make sure that's clear. It's a y. Okay? That is also easy to solve, right? Because if z is equal to 2, that's saying, let's substitute it in. That's really saying minus 3y minus 18 is equal to minus 27. Well, bring the 18 over to the other side, right? And what you're really saying is minus 3y is equal to minus 9, right? So y is equal to 3. And finally, the last equation here, the last equation says 5x plus 2y plus 1z equals 3. 5x plus, which is the original equation. I haven't changed this one at all. But now we know that z is 2 and y is 3. So we got here, we got 5x plus 6 plus 2 equals 3. So if we take 6 plus 2 at 8, subtract off both sides, you get 5x equals minus 5. X is clearly equal to 1. Sorry, minus 1. Duh, minus 1. Minus 1. Right? So, this is a nice way of really making life easier for us. Okay? We can actually solve this. Now, by the way, you can do this in Matlab. Okay? And I'm going to do it real quick in Matlab now, but I'm going to come back next time and we'll do it again some more in Matlab. I'll just show you some more stuff with this. Okay? Let me do this real quick in Matlab because, and then we'll go. There is a command in Matlab, and I think it's just like your REF commands in your calculator. Okay, this is just like your calculator, I believe. Try this in your calculator with the REF and see if it does it. I'm going to throw this in Matlab real quick. 5, 2, 1, 3, 4, 1, minus 1, minus 3, and minus 2, 3, minus 3, 5, right? And I'm going to do RREF of this matrix A. Oops. And there it is. Now that's the answer. If you were to keep going with Gauss and keep doing all the elimination all the way to this point, then it becomes very clear. The answer is given to you in that last column. Minus 1 is x, 3 is y, 2 is z. That's the answer. That's the answer to that system of equations. We'll go through, I'll show you how to do that matrix inverse way. I'll show you to solve this lots of different ways. And then all I want you to be able to do is to be able to take that problem, and instead of taking 10, 12, 15 minutes on a test, I want you to be able to solve it in 1 minute on a test, so you don't have all the time to take, you have more time to do other things. Okay? It should never be the kind of thing on a test that takes 15 minutes. Okay. This is